Isosceles triangles can be identified in two different ways. Firstly, by the fact that two of its edges are the same length, and that can be indicated by a slash across each of the edges that are of the same length. The other way of identifying an isosceles triangle is by noting that the base angles of the triangle are equal in size. Let's label the edges of equal length with an L. When we're asked to find the area of a triangle, the simplest way to do so is by using the equation area equals half base times height. But in this case, we run into difficulty because we have neither a base nor a height. We just have the length of the equal sides and the angles. So the equation in its current form isn't of much use to us. We have to find another way. I'm going to be more specific with the labeling of the angles and give them letters as their values. But notice that this still doesn't help us because we have neither a base nor height. So what do we do? It seems impossible, right? But there is a way, and that's by using an alternative equation. Here it is. Area equals L squared, that's the length squared, times sine of the angle A, all of that divided by 2. And that will give you the area when you don't have the height or the base, but do have the length of the equal sides and the base angles. The purpose of this video isn't to calculate any particular area of an isosceles triangle, but for us to figure out exactly why this equation works using some basic rules of trigonometry. And we'll actually be using half base times height along with trigonometry to finally arrive at this equation. So let's swap back to the half base times height equation and let's get started. One thing I don't particularly like about this setup is that we've got two variables, these two different angles of two letters. I want to be using the same letter so that we can work with this more easily. So what I'm going to do is I'm going to give A in terms of C. We know that the sum of all these three angles must be 180 degrees. So we can write that as 180 degrees equals A plus 2C, and that's the sum of our angles. But we want the value of A in terms of C, and we can do that by subtracting 2C from both sides so that 2C comes over this side. So that's 180 degrees minus 2C equals A. From now on, instead of referring to this angle as A, we'll refer to it as 180 degrees minus 2C. And this is going to be pretty useful later on. So now we've relabeled A as 180 degrees minus 2C. In order to use the half base times height equation for the area, we actually need a base and height. And so I'm going to create that. Let's bisect the top angle with a line that goes from the tip of the triangle to the base. It's called an angle bisector because it divides the angle exactly into two equal parts. The value of the entire angle is 180 minus 2C, but we want to divide it in exactly 2, and that's easy to do because 180 and 2C are both divisible by 2, so we could factor out 2 and call it 2 times 90 minus C. So each angle has the value of 90 minus C. Now that we have the values for our bisected angles, you'll see why I wanted to express A in terms of C. Notice first that we've created two triangles, and each triangle has two of the same values. The top is 90 minus C, and the outer base angle is C, which means the third angle of each must be the same. Let's call this angle X. It looks like a right angle, but we don't really want to do any guesswork. We want to show exactly what it is. We know that the sum of all three angles must be 180 degrees. So 180 degrees equals X plus 90 minus C plus C. Well, C and plus C cancel, and that just leaves that 180 degrees equals X plus 90 we subtract 90 from both sides, that leaves x on its own. So we get 180 degrees minus 90 degrees equals x. So obviously x must be 90, and both of these are right angles. So let's clean this up a bit, and we can put in our right angle symbols and the height and base of each triangle. The height of each triangle is just the dotted line, and the base of each triangle is the length that goes from the outside corner of the triangle to the dotted line. So that's the base of the right hand, and that's the base of the left hand triangle. Let's not forget to put in our right angles. And now that we have the right angled triangles, we're in a position to use trigonometry to find the base and height of each triangle. So let's start with the heights of both triangles, because clearly they share the same heights, so have the same value. You'll know from trigonometry that the sine of an angle equals opposite over hypotenuse. Well, we're using the angle C in this instance, so that means that sine of C equals opposite. Well, opposite is the height of the triangle, so that's h, over the hypotenuse. Well, the hypotenuse of this triangle is the length. In fact, it's the hypotenuse of both triangles. So sine of C equals h height over length. If we want to get the height, we simply have to multiply both sides by length, so that we get L sine C equals the height. So that's our height for both triangles. So let's write that down. You should know the cosine of an angle equals adjacent over hypotenuse. Again, we're using the angle C, so cosine of C equals adjacent. Well, this time the adjacent is the base of the triangle over hypotenuse, and we know that to be L. So if we want the base, we just multiply both sides by L, and we get that L cosine C equals our base. So let's write that. Are the bases the same length? Well, they must be, because L for this triangle is the same, because it's an isosceles triangle, and the angle is C as well. It's the same angle. So both these bases have the same length. Now that we have the base and height, we can plug those values into the basic equation for the area of a triangle. So we get that area equals 1 over 2 base. Well, the base you can see is L times cosine C times height. Well, height is L times sine C. We can simplify this a little bit. We've got 1 over 2. Because everything is multiplied, it doesn't matter which order you put them in. So we could put the L's together, and that makes L times L, which is L squared. And I'm going to put sine C first. Sine C times cosine C. But there are two of these triangles, so we times this by 2. The 2's cancel, so we get that the area of the entire triangle is L squared sine C times cosine C. This expression now contains trigonometric values. Let's move it over to the other side and compare it to the expression we're trying to come up with, the one I showed you at the beginning. So here's the one we came up with on the left, and here's the one we're aiming for, the one we claim is the expression that finds the area of an isosceles triangle. And you can see that they're different. The first difference is that the expression we've created with trigonometry has got sine and cosine, but the one we're trying to prove has got sine, no cosine, and then the angle we're using in the expression we came up with is C, but this one is A. So they're looking quite different at the moment, but there is something we can do about that, so that the angles in this expression are more closely related to A. And that's by figuring out the value of sine C and cosine C. We can do that using these two equations if we simply divide both sides of each equation by L. So we get that sine of C, well, if we divide both sides by L, that gives us h over L, height over L, so that equals height over L, or h over L. Then with cosine C, if we divide both sides of the equation by L, we'll get base over L, which equals b over L. So cosine of C equals b over L. Now I'm going to do something that does seem strange. I'm going to take the sine and cosine of this angle here. So we're going to be going that way. If you notice that sine of 90 minus C, which is the other angle, well, that is sine of 90 minus C is opposite, which is b, opposite over hypotenuse. So the hypotenuse is L. So that's b over L. And if we do cosine of the angle, that's going to give us adjacent, which is h, over hypotenuse, and hypotenuse is L. If you look at these two, you'll notice that they give the same value, b over L. So that means that cosine of C is exactly the same value as sine of 90 minus C, because both of them give b over L as their value. And the same is true of these two. Sine over C equals h over L, but cosine of 90 minus C equals h over L. Sine of C and cosine of 90 minus C is the same value. Now that means that we can rewrite this with the equivalent values of sine C and cosine C, which equals these two. So let's do that. It's L squared. It doesn't matter which way round we do these because it's a multiplication. So I'm going to do multiplied by sine 90 minus C, and that's multiplied by cosine of 90 minus C. And these two are exactly the same value. So we've changed the angle from C to 90 minus C. And 90 minus C is just another way of expressing A with a slight difference. So we're getting closer to the angle A. Now, if I was to plug L into here and C into here in this expression, and then plug A into this expression, we would get exactly the same answer, simply because this expression is just another way of writing this one. But how do I know this? Well, let's take a look at Wikipedia under the subject called Trigonometric identities. If we scroll down the page, and then we look at this equation here, it shows that 2 times sine of an angle times cosine of an angle can be rewritten as sine of 2 times the angle. And that simply means that these two expressions are identical. They're just different ways of writing the same thing, and this is called an identity. And I'm going to use this identity to prove this expression and this are the same thing. So I'm just going to paste a copy of the identity here, and I'm going to adjust it a little bit so that I can adapt it to this expression. If we divide both sides of the equation by 2, dividing this by 2, this cancels, so we get the sine of the angle times cosine of the angle equals sine of 2 times the angle over 2. Now this looks quite similar to this, doesn't it? Now looking at this expression, if we ignore L squared for a moment and say that our angle is 90 minus C, we can rewrite this using these angles. So let's see what happens. Well, that would mean that sine of 2 times the angle, well, that's 2 times 90 minus C divided by 2 equals sine of the angle, which is 90 minus C, times cosine of the angle, which is 90 minus C. But if we look at the angle inside the left-hand side expression, we have 2 times 90 minus C. Well, what is that? 2 times 90, that is 180 degrees, 180 minus 2c. And what is 180 minus 2c? Well, it is this which we looked at earlier on. It equals a, so that the angle in the right hand side expression is actually a. Let's correct that. And that means that sine of a over 2 equals this side of the equation which we had before, and now sine of a is part of the solution we were looking for. All we need to do now is simply add L squared back in to both sides. If you multiply both sides by L squared, so the expression that we figured out for the area of the isosceles triangle is actually just another way of writing this expression, which is L squared sine A over 2, which will give the area. So that proves that this can be used for the area of an isosceles triangle if you don't have height and base, but you have the length and all of the angles.